one more type of pruning that is actually very interesting and actually gets us talking about the stuff that we're going to be talking about next week, which is rule post-pruning. This is actually something that Quinlan added to C4.5, and wound up being what is used most of the time. It's a kind of a reduced error pruning, so it's a kind of post-pruning, but the interesting thing is that you prune the tree not into a tree, but into a set of rules. That's why it's called rule post-pruning. So what's going to happen is that I'm actually going to induce the tree not as the end goal, but I'm inducing the tree as a way to finally get a good set of rules out. Okay. And indeed, next week we're going to talk about just, inducing rules from scratch without worrying about decision trees. And then we'll compare the two. But you can also induce rules by first inducing a decision tree and then pruning it to rules. So let's look at three things in turn. First of all, what is the correspondence between decision trees and sets of rules? Okay. And second of all, how you prune a decision tree into a set of rules, and finally, why that might be a better idea. Okay? So, first of all, here's our good old friend, the decision tree for playing tennis. And the first question is, if I were to just convert this into a set of rules, so don't even worry about pruning for just a second, right? What would the set of rules look like? Remember, a decision tree is really a set of nested if-then statements, right? If outlook sunny, then if humidity high, then no, and so on and so forth, right? So it's a tree of if-then statements. A rule is just a statement of the form, if this and this and this and this, then play tennis. And then there's another rule that says, if that and that and that, then don't play tennis, and so forth, okay? So for every decision tree, there's an exactly equivalent set of rules, okay? So what is that equivalent set of rules? So for example, right, this is probably a very easy question, but nevertheless, let's go through it, right? So here's my decision tree, right? Give me one rule, sometimes called a decision rule, that you would get from it.
If overcast, then yes. If outlook equals overcast, then yes.
Yeah, brilliant. This is a really short rule, right? What's another one?
Outlook equals sunny, humidity equals normal.
Yep, here's another one, right? So if the tree has n leaves, how many rules are we going to have? N, right? There's going to be one rule per leaf, or per path in the decision tree, right? And the rule corresponding to a particular leaf, what are going to be the antecedents on that rule? What is it going to be testing? It's the attributes on the corresponding path of the decision tree, right? No brainer. And then the consequent is just the class prediction at that node. Okay? So for every decision tree, there's an equivalent set of rules. Okay? And I can turn one into the other completely mechanically. Okay? And indeed, when I do, so did everybody follow this? Yeah, straightforward. Okay? So, the first thing that I do when I do rule post pruning is I just take my final, full, big, noisy, overblown, overfit decision tree and convert it to the equivalent set of rules. Okay? So now, what do? You have your set of rules, you have your validation set of data that you've never looked at, and you want to come up with a better set of rules, right? So how would you do that? It's probably going to be somewhat similar to the, post-pruning that I had for decision trees, right? But what, and again, there's more than one way to do this, but, what's one way? Let's think about one rule in particular. Right? Let's take, a decision tree is one big, complicated, interrelated structure, but the rules at some level are all independent, right? So let's look at one rule, right? I have this rule here that tests a whole bunch of things, right? And probably some of them are noise, right? So how do I go about figuring out which ones to drop and which ones to keep? So remember, in the decision tree, right, what I did was I looked at each node and I tried pruning it, right? And then I pruned the one that gave me the biggest improvement, right? So in the case of a rule, what should I do?
Drop the one with the lowest.
Exactly. I look at dropping each one of the antecedents, right? And whichever one I get the most increase in the holdout accuracy from, I drop that one. And now I have a rule that's shorter, right? And then what do I do next? And I'll look at the remaining ones and drop the best one or the worst one, right? And when do I stop?
same rule as the tree, and the accuracy does not go up.
Exactly. When I try dropping every one of the attributes in my rule, and every single one of them now dropping it decreases my accuracy on the validation data. At that point, well, all those attributes seem to be doing something useful, so I'm done. Okay. So that's step 2. Are we done? This is actually where things suddenly get a little more interesting. So far, this was a fairly straightforward analogy to decision tree pruning, given this concept that we're going to produce a set of rules. But in the case of the decision tree, at this point we were done. In the case of the set of rules, are we done at this point? Is this a rhetorical question? Yeah, this is a rhetorical question. So why are we not done at this point?
The order of rules.
Why does the order of rules matter?
Which one should we evaluate first?
I have a bunch of rules that say yes, spam, and I have a bunch of rules that say no spam, right? And now how do I decide?
Performance.
One more time?
Performance.
Performance, sure, but more specifically.
I mean, some of the rules might take longer to evaluate.
Sure, I mean, sometimes that's a consideration, but usually the main consideration is accuracy, right? And some rules are more accurate than others, so what's a natural way to order the rules? The most accurate one first, right? So I order my rules, by accuracy, right? And then I just, the first one that fires wins. It's just an if-then statement with a lot of else's. If blah blah, then spam. Else blah blah, and some of these might be spam, some of them might be not spam. But as a heuristic, it's hard to disagree with the notion that I should put the most accurate rules first. Okay? There's in fact another thing that we can do that in fact works even better, but again we're going to talk about some of that later, which is what? Any way to make a different suggestion from picking and ordering for the rules?
You can tell that the majority of the examples fall under one rule, but that will work.
Exactly, majority, we vote. Remember? Learning algorithms like democracy. They like the wisdom of crowds. I have a bunch of rules. Some of them say yes, some of them say no. Let them all vote, and the one with the most votes win. Should all rules have the same weight, or should some rules have more weight than others?
Simple one should have heavier weight.
Yes, certainly if you believe in simplicity as a heuristic, that's something that you should use, right? But what's another thing that you should use for the weight? That's even more obvious. And in fact, you could combine the two. Right? Remember, when we were ordering the rules, we put the more accurate ones first, right? In a way that's like saying the first rule has more weight than all the others put together, right? So what's something that I could weight my rules by when I'm voting?
Accuracy.
The accuracy, yeah. In fact, what people typically use is a combination of the accuracy and not the simplicity, but the coverage of the rule. The coverage of the rule is how many examples in the training set does it account for? What might the reason for that be? Why would, given two rules with the same accuracy, why would I prefer a rule with more coverage? Right, let's say these two rules are both 100% accuracy. This rule here is 100% accurate on 2 examples, and this one here is 100% accurate on 2,000 examples. Which one would you prefer?
More generalizable.
The one on 2,000 examples, because
You can generalize.
that one I have confidence in, right?
Yeah.
If you got 2 examples right, you got lucky, for all I know. If you got 2,000 examples right, it probably wasn't luck, right? But again, there's many combinations of these things that you could use, but those are 2 good things to use.
I still not get the prove each rule independently. It's like we have each path as the rule. Now how are we pulling it? Like we are removing an attribute and checking. Like I did not get that part.
No, so very good. So this is actually another point that I was about to bring up. So why? So let me actually backtrack for just a second, and then we'll get back to this. Why did we have to do this for the rules, but not for the decision tree? In the decision tree, we didn't have to pick an ordering or vote among the leaves or any of that. Why was that?
There's no choice in a decision tree.
Because notice what, the rules that you get by directly translating a decision tree have a very, very unusual property. That set of rules, right? The set of rules that I got from this tree has a property that most rule sets don't have, which is this is not, immediate to see, so let me just say, right? Only one rule ever fires. The property that the decision tree has is that the paths to the leaves are all mutually exclusive. In the assumption of full data, right? There's no missing data. You can only go down one path, which means that, if this rule matches, then this one for sure cannot. And when I prune the decision tree, all I'm doing is shrinking it towards the root, right? What is the big difference between that and what happens when I'm pruning two rules? This is a subtle point, but it's actually crucial, right? If I was pruning the decision tree from the leaves to the root, right, I would consider pruning humidity, right? And then I would consider pruning wind, right? And if I had actually pruned these, then I might consider pruning outlook and having no tree, right? That would be bad, but it could happen, right? But here's something that would never happen, right? I would never prune outlook without pruning humidity and wind. You agree? There's just no way to do that, right? Because the outlook is what actually splits me into disjoint sets. And then I get more splits and so on and so forth, right? So decision trees have this advantage that applying them to the test example is actually faster, right? It takes essentially logarithmic time, right, to just fall down to a leaf. Whereas a rule, you have to keep matching them until, they're not going to match, right? So decision trees are faster to apply. However, pruning two rules tends to give a more accurate model than pruning two decision trees. Why?
Might discover something like if the humidity is normal, the outlook doesn't matter.
You get rid of noise?
Yeah, keep going. Anything else?
You also prune on attribute values instead of attributes.
Very good. So let's try to synthesize this, right? Notice that when I'm pruning two rules, let's think about, a particular one of these paths, right? When I'm pruning the decision tree, what I have to do is I either prune humidity, or then I prune, or, by the end of the process, I have pruned humidity and outlook, right? So all I can do is shrink the path from the end to the beginning, right?
So what do you mean by pruning humidity? It's like removing that rule?
Yeah, I'm removing this and I just, I predict, once I'm sunny, I just predict, let's say, yes. Okay? Right, so I get rid of that, right? So when I'm pruning to a decision tree, I'm very constrained in the things that I can prune. When I'm pruning to a rule set, given one rule, I can prune any attribute that I want, right? In particular, once I have this rule, if outlook sunny and humidity high, then play tennis snow, right? If you look at pruning the decision tree, I can prune humidity, but I can't prune outlook, or I could prune both. But when I'm pruning to a rule, sure, I can prune outlook, right? So I can prune more things in the case of the rule than in the case of the decision tree. And now, why might this be a good idea? All right, notice the following. Outlook is the thing that we're stuck with here, right? And outlook, the thing that happens here is that outlook is tested in every single rule. Boy, that outlook attribute has to do a lot of work. Suppose that outlook is good for some rules, but not others, right? In the case of the decision tree, well, I'm stuck with it. I have to take the good with the bad. In the case of the rule set, no, I can prune it from some rules, but not others. Okay? So you tend to get a better model when you prune to a rule set. A more accurate model. In addition, and sometimes this is actually the biggest reason, you also tend to get a much simpler model. You run C4.5, you can do this experiment yourself. Run C4.5, do the post-pruning to a decision tree, and do the post-pruning to the rules, and then decide whether you'd rather be looking at the decision tree or the rules. The set of rules, if you give a cost of 1 for each antecedent in each rule, and the cost of 1 for each field in the decision tree, the set of rules is going to tend to be much, much smaller than the decision tree. Why is that? Remember, in the decision tree, this lower part of the tree, I'm always going to have it there, right? The rules, I can actually get very short rules, each of which just uses the 2 or 3 attributes that are really good. In the decision tree, I'm stuck with using outlook for everybody. And then, when Outlook is, say sunny, I'm then stuck using the entire next subtree for everybody. Okay? So by pruning to rules, I can get A, more accuracy, and then B, a much smaller and easier to understand model. So it's no wonder that people often prefer to have a rule set. It does have some disadvantages. It will typically be more expensive to learn, and when you're on a large data set, that is an important consideration. It will be more expensive to apply. And in some domains, applying things very quickly. In some domains, it doesn't matter. In some domains, that's a big constraint. Okay? And it's also, the decision tree pruning is fairly straightforward. Pruning to rule sets, is a little bit, there's more things that can go wrong. Okay? So there's pros and cons, but it's definitely worth knowing about pruning to rules. Okay?
So once you get to rules and prune, you can't go back to a decision tree, right? You have
That is a good question. In fact, we're going to talk about this question next week. So I propose that you think about it, and then you can tell us what you found next week. This is definitely a very interesting question, right? Think about this. If I have a set of rules, right? Can I convert it back to a decision tree? If so, how? And what might be the pros and cons of doing that? Yeah.
I think as the post-pruning process is more complicated, you have more attributes and stuff. Is there a risk of fitting
precisely.
to the test date validation data?
Exactly. Very good. Yeah. This is machine learning thinking, right? Is that, sure, it's more powerful, I can learn more things, but you should also be thinking, well, now I have to make many more choices. So if I have a large, rule set and I do a lot of stuff, now maybe I'm overfitting my validation data. Exactly. That's why you have to be more careful. So if you're not careful, you could, do rule pruning, and you try so many things that you're now overfitting your validation data. By the way, here's a quick, question. When you're splitting your training data into training and validation sets, whether you're going to use decision trees or rules, what relative size should they be? 50-50? Should use more data for training? Should use more for validation? What is your feeling?
90-10 training?
Sorry, you said more for training?
90-10.
90-10.
Oh, 90-10. Okay. So, but 90 for training and 10 for testing is what you're saying.
Yes.
Okay. Anybody disagree?
And the other way around.
less for training, more for.
Less for training, more for testing. Why?
So that will reduce the complexity, or as well as we get a chance to prune and.
No. So you're arguing for less pruning data or more pruning data?
I'm arguing for more test validation and less training data.
Okay. Because
that way our complexity is less and we get a chance to prune it and we have more data to validate.
do you agree?
Yeah.
Okay. So what's the argument for more training data?
You get a better model to start with.
All of these arguments have some merit. And anybody, okay, so 2-1 right now. Who else wants to weigh in? Who feels lucky today?
50-50.
That is a total, very excellent. Now we have all the options on the table. Sure, 50-50. What's the argument for 50? That's a totally reasonable thing to suggest, right? What's the argument for 50-50?
Both sides have, both the arguments have
Merit that,
But do they have equal merit? And more importantly, are there bigger arguments that have not been made yet? What you just stated is the famous principle of indifference. Formulated by Monsieur Laplace back in the 19th century, which is when you don't know, just 50-50, right? You're indifferent. But better, so if you have to do things in a short time, that's a reasonable thing. But now let us think about what might be better, right? Anybody else want to weigh in?
Well, it seems like there's also a question of how much data you have. If you only have a small set of training data, then, a small set of data you can work with, then maybe you want to go 90% with your training. But if you've got a huge set of data you can work with, maybe you only need 10%.
Another very good point. So let me synthesize that as follows. The trade-off is not necessarily independent of the data set size. In fact, it might change as the data set changes. In fact, if I have a ton of data, what should the split be? I don't care. Right? I have a ton of data either way, right? As long as it's not epsilon versus 1 minus epsilon, with a lot of data, it doesn't really matter. So this is really a crucial question when I have very little data. Yeah?
This may be way out on a limb, but could you start with a small amount of training data and a lot of validation data and see if the model works well, and if it doesn't, then gradually increase the amount of training data until you find a model that fits well?
You could, but that's a little dangerous, right? Because now you're starting to use the validation data as more training data, right? The thing about validation data is that you have to use it infrequently, and that might not be too frequent, but it's a slippery slope. Okay, any other thoughts?
It seems to me like selecting the training data set. If you're selecting a small piece, depending on which piece you select, that could really change your whole decision tree. So how could you compare?
So you vote for more training?
I vote for more validation, actually.
Oh, okay. So 3-1. Anybody else want to say something?
But your argument of decide later.
I'm enjoying this.
The other argument is decide later. So you first train yourself and then decide later.
You should go into politics. I see you rising high above in the ranks of management. But we're just engineers here, so let's try to not go that route.
I mean, if you get good accuracy with a small training set, I think, and maybe that's what you're saying earlier is, and that's pretty good enough.
Actually, let me just put a thought into the air, right? Let me ask you this question: which one is harder, learning the initial, tree from data, or pruning a tree to the best subtree? Which one do you think is harder?
Pruning is harder. That we have more roots and.
Is it?
Because we have so many paths.
Let me actually jump ahead, right? If pruning is harder, then we should use more data for pruning, right? Because we want to use more data for the harder thing, right? Does everybody agree? Whichever is hardest is what we should reserve most of the data for, right? Because that's where it's needed. But which one is harder? Is it pruning or training, right? How do we decide this? Well, let's think about it this way. Which one do you have more? This is a search problem, right? It's an optimization problem. I have a search space of decision trees, right? What is the search space for learning and the search space for pruning? Actually, the search space for pruning is clear, right? It's just the space of all subtrees of that tree, right? What is the search space for learning? It's every decision tree in the universe, right? So which one is larger? Which space is larger, the space of decision trees when you're learning, or the space of decision trees when you're pruning? When you're training, and by a lot. It's way larger. So, anyone care to revise their vote? Is that your final answer? This is the kind of thinking that you have to do when you apply machine learning. Once these things become a pattern, then one day they just become part of a class that you get to take. But right, you can acquire this experience empirically. Right, people started out doing splits of various kinds, and indeed, so let me jump right to the punchline. And what do people usually do? They always have a bigger percentage of the data for testing, right? The percentage varies, and one of the ways in which the percentage varies is with how much data you have. If you don't have a lot of data, right, then then you're really stuck, right? But then you lose. Remember, you're in that early part of the learning curve. You lose a lot by reducing your training set, right? On the other hand, your validation data is going to be very noisy too. Okay? As you get more and more data, things become very, very easy in both directions, right? So typically, what people wind up using is something like 2/3, 1/3. This is empirical, right? There's also a lot of theory about this, but empirically, this is what people tend to use: is 2/3, 1/3, or 3/4, 1/4, or 90/10.
90 for what? 90 for
90 for training and 10 for pruning.
Oh.
Now, when you're really, really short of data, there's something you can do called cross-validation. Has anybody heard of cross-validation?
It's where you have, you pick one set of data for training, one set of data for validation, and then you pick a different set of data for training, a different set of validation.
It's a very clever idea. Yes, roughly speaking. Now let me say a little bit more precisely. It's a very clever idea where you actually get to use all the data for both training and testing. Isn't that amazing? Here's what you do. Let's say you do 10-fold cross-validation. This is probably the most popular. You divide your data randomly into 10 pieces. And then what you do is you train on 9 and you test on the 10th. And you see where this is going next? Then you pick another piece that you hold out, you train on the other 9, right? So all of them rotate through being, you form 10 different training sets, each of which contains 9/10, and then you test on the remainder. So at the end of the day, right, you basically, every data point got to be used as training and testing. What you did was a bunch of runs where you had a 90-10 split, right? This is good, that everybody got to be training 9 times and everyone got to be testing 1 time, right? The disadvantage of this is what? There's 2.
You're doing the work 10 times over. So
Yeah, it's expensive, right? You just increased your running time by an order of magnitude. Ouch. The other problem is that, well, so what do you get out of those runs, right? You can't be, at the end of the day, what is the decision tree that you produce, right? You just learn 9, right? Which one? So what people typically use cross-validation for is things like picking the value of that complexity penalty. How much should I weigh the complexity versus the accuracy? Well, let's use cross-validation for that. Let's see what's the coefficient that gives me the optimal trade-off, right? I can do that using my cross-validation, and then once I found that coefficient, now I run on all the data and I give it to my customer and I pray. This is a very common machine learning strategy. Okay. All right, questions about any of this? Okay, there's one more important thing to touch on before we're done today.